In this lecture, we're going to talk about the ionization of acids and bases. So what's happening when an acid or a base interacts with water molecules? So the acid ionization constant is its own special symbol, and that is the Ka. And it is just the equilibrium expression for the acid ionization or dissociation of the acid into the H3O plus and its conjugate base. Now, keep in mind, this is not the same ionization energy that we talked about with atoms losing electrons. We are talking about losing a charged proton. So H plus is lost, it's gained by water to give us H3O plus and A minus. H plus doesn't really exist in solution, so we are going to use this terminology for this lecture. So we can set up our K expression for this equation, and we get the concentration of acid multiplied by the concentration of the conjugate base divided by the concentration of the acid itself. And so we don't include water as it is a pure solvent. And so this tells us that if the Ka value is large, there's more dissociation because we would have a larger number on top and a smaller number on the bottom. That would lead to a bigger Ka. Acids with low levels of dissociation, so if the equilibrium lies far to the left, then this Ka will be small. Strong acids undergo complete ionization, so the concentration of Ha is essentially 0, which means that we don't really have a Ka for the strong acids in water because they fully dissociate, so this expression is meaningless if you have a 0 in the denominator. So the relative strengths of our acids, if we were to compare these three, so here we have acetic acid. It has a Ka value of 1.8 times 10 to the minus fifth. And here is the second proton in HSO4, so sulfuric acid. So you might want to watch the polyprotic acids lecture if you're curious about this. So that second ionization has a Ka of 1.2 times 10 to the negative 2. So this is a stronger acid than this one. The other way to consider the strength of an acid is the percent ionization, which is the concentration of the H3O plus divided by the Ha multiplied by 100. So keep in mind that this here is the equilibrium concentration of the acid, and this here is the initial concentration. And so the initial concentration of your acid that you threw into water and the equilibrium concentration of H3O plus. So let's practice by calculating the percent ionization of a 0.1 molar solution of acetic acid with a pH of 2.89. So we set up our percent ionization equation where we have our H3O plus and our CH3COOH. So this is acetic acid and hydronium. And we get our hydronium ion concentration from the pH. So remember that the P function means to take the negative log of something, so we do the inverse. So 10 to the negative 2.89 equals 1.29 times 10 to the minus third. So now we know both components of our equation. So we set up 1.29 times 10 to the minus third divided by 0.1 multiplied by 100, and that gives us 1.3%. So this shows us that this reaction lies pretty far to the left. So if you wanted to use Le Chatelier's principle to increase the concentration of the H3O plus, you would have to add something that would cause that to happen. So there's also a base ionization constant, and this is really similar to the acid ionization constant, where you have your base and then the base steals the proton from the water, increasing the concentration of hydroxide ions. You can think of this like ammonia, where you have NH3 and then NH3 plus and hydroxide. So our Kb value is the protonated base, so the conjugate acid, multiplied by the hydroxide ion concentration divided by the base concentration. We do not include water as it is a pure solvent, and larger Kb values indicate more dissociation, just like we discussed with the acids, and strong bases essentially undergo complete ionization, just like strong acids, so that means our denominator is essentially 0 or 0, and we don't have a Kb value for strong bases. So the relative strength of these bases here, we see our top base here, the NO2 minus, has a Kb of 2.17 times 10 to the minus 11th. So it is this is very unlikely to steal a proton from water to make hydroxide. So that's what weak base means. So you're more likely to find this in solution than you are this. As you moved down here, we see that ammonia is the strongest base listed here. And much like with acids, we can look at the percent ionization of a base. And here we have our hydroxide at equilibrium divided by our initial concentration of base. Okay, so let's look at this relationship between Ka and Kb, because this relationship is extremely useful when thinking about what's going on inside a vessel containing acids and bases. So here we have our Ka expression and set up for our equation showing the dissociation of an acid. And here we have our Kb expression set up to show the deprotonation of water by a base. So we can actually add these two equations together. So we are taking these four components here, and they're all here on this side. And then we cancel the ones that are the same on both sides. So all four of these are here, and we've canceled those. So now we're left with 2H2O to H3O plus and OH minus. So once we've done that, we actually have to multiply the K's. So the rules are when you add an equation together, you multiply its constants together. So we can get a new constant now, and that new constant is the Kw. So we cancel the conjugate base, we cancel the acid, and we're left with proton concentration multiplied by hydroxide concentration equals the Kw, which is 1 times 10 to the minus 14th. The Kw is always 1.0 times 10 to the minus 14th. That's why pH 7 is neutral, because this is 1.0 times 10 to the minus 14th, which means that these have to be 1 times 10 to the minus 7th, which is a pH of 7. Lastly, we can relate our Ka to our Kb values, where Ka equals Kw over Kb. And similarly, our Kb value is equal to Kw over Ka. So this means that if you know either Ka or Kb, you can find the other one because we always know Kw. So I hope that this was helpful in understanding the relationship between these constants that help us interpret what's going on inside a vessel where these acid-base reactions are taking place. The take home here is to understand how this expression arises and how to use our Ka and Kb values, and also to use those Ka and Kb values to interpret the strength of acids and bases.